Okay, so one thing to always remember is that any information you get before any of the sort of sub-questions, so for example, here we say it's telling us that this is a question about nitrogen and some of its compounds, and that information comes before any of the sort of question parts. One of the things that is highlighting is that is relevant to all of the questions. So all of the questions are related in some way to bonding and nitrogen. So then we move on to the very first question, and it says nitrogen reacts with lithium to form lithium nitride. Now, one of the things that possibly could leap out to us straight away is that if we have, and it's a rule of thumb, so it's not absolutely perfect, but if we have a metal and a non-metal reacting together, then we are forming an ionic compound. And in fact, actually, it makes that clear in the next line because it says lithium nitride contains the nitride ion N3-. So they've explicitly stated now that we're talking about an ionic compound. And remember that right at the beginning is they were saying that a lot of this question was related to bonding. So then it's giving us essentially three questions. So it's asking us about to give the full electronic configuration of the nitride ion, to deduce the formula of lithium nitride, and finally to explain why lithium nitride has a high melting point. So giving the full electron configuration of the nitride ion, as we already seen, they've given us the formula of the nitride ion. They said it's N3-. So what that 3- means is it's had or it's got 3 extra electrons compared with a nitrogen atom. So CF compared with nitrogen. So we look at our periodic table, and we look at nitrogen here, and we can see that the atomic number is 7. So nitrogen has 7 protons, and therefore a nitrogen atom would have 7 electrons. But this 3- here is telling us that we have 3 extra electrons. So we have 10 electrons in total. Which equals 10 electrons in total. So when it comes to our electron configuration, we've got to remember the order that we fill the subshells up in. So we have 1s and then 2. We have 2s and then 2. So we've got 4 electrons so far. And then we've got 2p6, and that is our 10 electrons. And one of the things to remember as well is that, at GCSE, you talked about gaining, losing, sharing electrons when it came to bonding. And probably you were told or taught or whatever that essentially what was the consequence of all of that was that you got a full outer shell, and really that's no real difference here. Or another way to think of it maybe is not just that it got a full outer shell, but it achieved in sort of a noble gas configuration. So that's perhaps the way of thinking about it here. So we've achieved a noble gas configuration. We've achieved the electron configuration of neon. Then it asks us for the formula. So, again, this is a sort of, these questions so far are very much relying on GCSE knowledge and then perhaps a little bit of A-level on top. But this question here, we should or could have been able to work out if we were sort of secure in our GCSE knowledge. So we know it's an ionic compound. And one of the things that the periodic table helps you with is if you know that ions are formed, then you should be remembering that group 1 forms +1 and group 2 forms +2, and anything in group 3 that forms an ion is going to be +3, and then working backwards -1, -2, -3. And in fact, and that's what we've got with nitride ion. We've got an N3-. When you're coming up with any sort of compound formula, there's never an overall charge. So the sort of ratio of each ion, your positive ions to your negative ions, the ratios are such so that the charges cancel out. So we've got a 3- charge on our nitride ion, and if we look on our periodic table at where lithium is in group 1, so lithium is going to form a 1+ charge. And so if we're going to achieve an overall charge, if you like, of 0 in terms of our ratio of ions, then we need 3 1+s to cancel out the 3-. So our formula is going to be Li3n. And then the question asks us, explain why lithium nitride has a high melting point. And this is about thinking about, again, this is a GCSE question, essentially. You know, why is it that ionic compounds have high melting points? Why is it that ionic compounds are solids at room temperature? Because in a sense, the state of matter at room temperature is, in effect, an indication of the forces of attraction that have to be broken or overcome for something to change state. So we have an ionic compound, and it's probably been drummed into you that there is a strong electrostatic, and the strong bit is important, okay? Because it's not everything is going to have electrostatic forces of attraction in chemistry, in any bonding, sorry, but whether they're strong or weak is going to determine how much energy is required to change state, because we are basically having to overcome those forces of attraction. So there are strong, so missed a word there. So there are strong electrostatic. You don't need to put the electrostatic because they will just allow forces of attraction. So there are strong forces of attraction. And then, you know, you've got to think, well, what are they between? So obviously they're between opposite charges, but what those opposite charges, the species, if you like, that have those opposite charges can vary, and these are between, and you can say positive and negative ions, but let's just be really specific here, between the lithium plus ions and the N3- ions. Oops. It's between the opposite charges. So we got 4 marks in this question. Obviously, that was 1. The electron configuration, obviously, that's 1. Then it's the strong forces of attraction is a 3rd mark, and then saying what it's between is the 4th mark. Okay, so the next question, it says the structures and boiling points of hydrazine and nitrogen are shown. Explain in terms of structure and bonding why the boiling point of hydrazine is higher than the boiling point of nitrogen. So bonding, there are only really three types of bonding, really. Okay, covalent, metallic, and ionic. But when it comes to structures, there are essentially 4. So there's ionic structures, there are metallic structures, then there are giant covalent structures, and then there are molecular structures. Now, if you have got covalent bonds and they don't just carry on, so you are able, in effect, to show where the structure ends, which is what we're able to do here. We can show that the structure, these are like boundaries to the structure, if you like. And we know it's covalent bonds, then we are talking about molecular substances here. And whenever we're talking about the boiling point or melting point of molecular structures, then we are talking about intermolecular forces, okay, forces between molecules. Okay, so we're what's relevant here, so the bonding they're really talking about, so it's a little bit, I don't feel it's completely the right term they're using, but we're talking about intermolecular forces. So there has clearly got to be a difference in the intermolecular forces between when it's hydrazine and when it's nitrogen, because we have a very large difference in boiling point, over 300 degrees Celsius. That's a significant difference. So the thing is to do is to consider what intermolecular forces are relevant for each one. Now there are three intermolecular forces. So put IMF. So there are three possibilities. There are van der Waals, there are permanent dipole, and there is hydrogen bonding. Now everything has van der Waals forces. And we do know how the van der Waals forces can vary. They can vary depending on the MR, or essentially the number of electrons, but the MR is a reflection of the number of electrons. So the MR of the molecule. And what I would say is, if we're comparing van der Waals forces in an exam question, you're only going to make a direct comparison between van der Waals forces if they are the only intermolecular forces in those molecules that you're comparing. So if we're able to differentiate the molecules according to the remaining intermolecular forces, the permanent dipole or the hydrogen bonding, then that's really what we need to focus on. But you should always state what each of them, what every molecule has. Now, permanent dipole is a consequence of a difference in electronegativity between atoms. And really, when we're talking about molecular substances, we're talking about non-metals. And so we're really considering whether there's nitrogen, oxygen, or a halogen. They're really the elements that are going to lead, typically, as long as they're bonded to something different, they're the ones that are going to lead to a difference in electronegativity, and therefore a dipole. And then we have to consider the shape of the molecule to decide whether the dipole is permanent or not. And then finally, hydrogen bonding. And I think this is the one where quite often people get caught out, because we've got the comment about you've got to obviously have hydrogen, and then it's one of the three most electronegative elements, so nitrogen, oxygen, or fluorine. And people will often just try to look for those two things and then go, right, there's hydrogen bonding. But it's really important that you really understand the definition of hydrogen bonding, and that is hydrogen is bonded to nitrogen, oxygen, or fluorine. It's not that the molecule has hydrogen and one of nitrogen, oxygen, and fluorine. It is that the molecule has hydrogen bonded to nitrogen, oxygen, or fluorine. So what we can see, if we look at the hydrazine molecule, we can see that we do have hydrogen bonded to nitrogen. So hydrazine has hydrogen bonding. Now, it's not enough. You've got to be very careful to just leave it at that you don't just leave it at that in terms of even just talking about hydrazine. Hydrazine has hydrogen bonding. And what are we talking about here when we're saying hydrogen bonding? We're saying about a force of attraction between molecules. These are intermolecular forces, and you need to spell out that you recognize, because they haven't told you that these are molecules. You have deduced it, and you shouldn't make assumptions that it's there in the question, it's implicit. No, you have to make it explicit. Hydrazine has hydrogen bonding between molecules. That is absolutely essential. That shows the examiner that you understand what hydrogen bonding is a force of attraction between different molecules. Obviously, it's going to have van der Waals, and then we could write that. So hydrazine has hydrogen bonding and van der Waals forces between molecules. Nitrogen. So nitrogen, yes, that is one of our very electronegative elements. But when you have two elements that are exactly the same bonded to each other, there is clearly no difference in electronegativity. So there is no dipole. There's no partial charge. There's no delta plus, delta minus. That's what all of those terms I've just said meant. So in the case of nitrogen, nitrogen has van der Waals between its molecules. So we're just treating those two molecules at the moment separately. We've stated a fact with hydrazine, we've stated a fact with nitrogen, and now what we need to do is say, right, okay, well, what's the consequence of those, the consequence of each of them having it? Why is it that that has led to hydrazine having a higher boiling point? Well, hydrogen bonding is stronger than van der Waals forces. And what that means is then that more energy is required, but that wasn't necessary for this mark. But sometimes, just, you know, if you're not sure, or you think it's 4 marks, then the final thing to that would be, so more energy is required to separate or to overcome the forces of attraction in hydrazine than they are in nitrogen, so there is a higher boiling point.